Where are we heading in this vast cosmic ocean? What unseen forces chart the course of entire galaxies, and what mysteries lie hidden beyond the stars? Is our journey through space a mere drift, or is it guided by something far greater, an irresistible pull toward the unknown? In the infinite expanse of the cosmos, nothing stands still. Every star, every planet, every galaxy is caught in a perpetual motion, bound by the gravitational currents of the universe. Yet, amidst this endless dance, there is something peculiar about the movement of our Milky Way galaxy. Astronomers in the 1970s made a discovery that would challenge our understanding of the cosmos and ignite decades of investigation. The Milky Way, it seemed, was not just orbiting within its own cluster of stars. It was moving, and not just moving, hurtling along with countless neighboring galaxies toward a specific point in space. But this was no ordinary destination. Hidden behind a thick veil of gas and dust known as the zone of avoidance, it remained unseen, a mystery cloaked in darkness. It was as if the Milky Way, like a small raft adrift in a vast ocean, had been caught in a powerful current, drawn toward an unseen force of staggering proportions. Two astronomers, R. Brent Tully and J. Richard Fisher, sought to unravel this enigma. Using the Parkes radio telescope in Australia, they mapped the motions of distant galaxies. The patterns they found were striking. These galaxies all seemed to be heading toward the same general region of space. Around the same time, other researchers were studying the cosmic microwave background, the faint afterglow of the Big Bang. By analyzing its temperature variations, they uncovered another clue, a subtle imbalance in its warmth across the sky. This imbalance wasn't random. After accounting for the motion of the sun around the center of the Milky Way, a residue remained, an additional velocity of hundreds of kilometers per second. It was as though our galaxy, and the galaxies around it, were being tugged by a vast gravitational force, one that could stretch across tens of millions of light years. The only problem? We couldn't see it. It lay buried behind the zone of avoidance, an invisible beacon pulling us closer with every passing moment. Astronomers gave it a name as enigmatic as the force itself, the Great Attractor. It was a fitting title for something so powerful, so mysterious. This singular point in the cosmos seemed to pull not just the Milky Way, but entire clusters of galaxies containing hundreds of billions of stars into its gravitational embrace. It was a cosmic sink of gravity, a point where the ordinary rules of motion no longer seemed to apply. And yet, as strange as this may sound, this is far from unusual in the universe. The cosmos is a dynamic, restless place. Our Earth orbits the Sun orbits the Milky Way's core, and the Milky Way itself is just one part of a larger cosmic web. Everything is moving, and everything is being pulled by something greater. The Great Attractor is no exception. It is part of a grander cosmic flow. Over the years, astronomers discovered that this mysterious force is merely the tip of an iceberg, a vast structure of unimaginable scale. It is connected to even larger patterns of motion, including the Laniakea supercluster, an enormous web of galaxies that spans over 500 million light-years. This revelation raised even more questions. What is the Great Attractor? Is it the remnant of a colossal black hole, a dense region of dark matter? Or perhaps something even stranger, a feature of the universe we have yet to comprehend? For now, the answers remain elusive, hidden behind the veil of interstellar dust and the limits of our technology. But the search continues. Astronomers are developing more powerful instruments capable of peering through the zone of avoidance and mapping the unseen structures of the universe. They hope to uncover the true nature of the Great Attractor and the forces driving this cosmic flow. What they find may reshape our understanding of gravity, dark matter, and the very fabric of space-time. As we gaze into the cosmos, we are reminded that we are part of something much larger than ourselves. Our galaxy, our solar system, our planet, all are participants in this grand celestial journey. We are moving, together with countless stars and galaxies, drawn by forces we cannot yet fully explain. And so the question lingers, where are we going? What lies at the heart of this gravitational mystery? And will we ever truly understand the forces that guide us through the universe? Where are you going? Motion defines the universe. It is the thread that weaves the fabric of our existence, shaping everything from the smallest particles to the largest cosmic structures. Science, in many ways, is the story of our growing awareness of this cosmic restlessness. For millennia, the brightest minds in Europe and the Middle East believed the Earth was a stationary center of the universe, with the heavens revolving around it. Early astronomers worked tirelessly to explain and predict the motion of celestial objects, the sun, the moon, planets, and stars. Their models, intricate and complex, managed to describe these movements with surprising accuracy. Yet, beneath this success lay an unwieldy system, filled with nested circular orbits and countless mathematical adjustments. In 1543, on his deathbed, Polish astronomer Nicholas Copernicus published On the Revolutions of the Heavenly Spheres. This work proposed a radical restructuring of the cosmos. In Copernicus's universe, the sun stood at the center, still and immovable, while the Earth and the other planets orbited it. This heliocentric model promised a more elegant explanation of celestial motions, but left lingering questions. If the Earth moved, why couldn't we feel it? Where was the great rush of wind? Why weren't we flung into space by the Earth's incredible rotation? It took centuries of scientific progress, culminating in Isaac Newton's theory of gravity, to address these questions. Today, we understand that we do not feel Earth's motion because we are part of it, moving together with our planet through the vacuum of space. Without an atmosphere to push against, our motion remains imperceptible to our senses. But this realization posed another challenge. How could we be certain that the Earth truly moved? What was the standard frame of reference? Newton assumed the existence of a universal frame of reference, an absolute ruler against which all motion could be measured. However, Einstein's theory of relativity overturned this idea. In Einstein's universe, there is no absolute reference point. Motion is always relative, measurable only in relation to another object. This principle gave rise to the fabric of space-time, the equivalence of mass and energy, and the immutable speed of light. Imagine drifting in a rocket through the void, encountering a friend in another unpowered ship. Both of you are moving at constant speeds, each claiming to be at rest while the other moves. Relativity tells us that both perspectives are equally valid. Even so, we can infer the Earth's rotation from phenomena like the Coriolis force, which shapes weather patterns into spiraling hurricanes. Without stars to guide us, we could still deduce Earth's spin by observing its effects on the physical world. However, understanding Earth's motion within the larger universe requires more. We need a cosmic yardstick, something to measure against. Thankfully, the universe's expansion provides just that. The cosmos is not static, but stretches over time, its galaxies drifting apart like ink dots on an inflating balloon. This expansion gives us a preferred frame of reference, a universal flow against which deviations can be measured. These peculiar velocities, distinct from the general outward motion, help us understand not only Earth's place, but also the intricate dance of galaxies. On Earth's surface, motion is staggering. Depending on your location, you may be spinning at up to 1,600 kilometers per hour due to Earth's rotation. Over an average lifetime of 80 years, this adds up to 1 billion kilometers. But this is only the beginning. The Earth orbits the Sun at an average speed of 30 kilometers per second, traveling an astonishing 80 billion kilometers in a human lifetime. These orbits, though immense, are circular journeys that lead back to the same point. We're moving, but not really going anywhere. Yet our solar system, carried by the Sun, is also in motion within the Milky Way. Orbiting the galactic center at an average speed of 230 kilometers per second, it takes 230 million years to complete one revolution. This incredible speed provides compelling evidence for the existence of dark matter. The visible matter in the Milky Way, stars, gas, and dust, is insufficient to account for the gravitational forces holding the galaxy together. Without dark matter's unseen mass, the Sun's velocity would have ejected it from the Milky Way billions of years ago. Beyond its orbit, the Sun oscillates through the galactic plane like a buoy bobbing on a dark sea. Influenced by the gravity of neighboring stars, it rises and falls thousands of light years over millions of years. At present, the Sun is plunging through the local bubble, a vast low-density cavity in the interstellar medium created by ancient supernova explosions. This journey through the bubble, which spans about 1,000 light-years, will continue for several million more years. And yet, this too is part of a larger story. The Milky Way itself is in motion, heading toward our nearest galactic neighbor, Andromeda. These two galaxies, drawn together by mutual gravitational attraction, will collide in roughly 4.5 billion years, merging to form a new galactic structure. This cosmic ballet is a testament to the universe's restless dynamism. But even this colossal interaction is not the final word. The Milky Way, along with Andromeda and other members of the local group, is being pulled toward a region of immense gravitational influence known as the Great Attractor. This mysterious force, obscured by the dense gas and dust of the zone of avoidance, tugs on entire clusters of galaxies. The Great Attractor is itself part of an even larger structure, the Laniakea supercluster, a vast network of galaxies spanning over 500 million light-years. Billions of years from now, the night sky will be unrecognizable. The moon will have drifted farther from Earth, appearing smaller and fainter. The sun, swelling as it exhausts its nuclear fuel, will burn larger and brighter. Familiar constellations will dissolve, replaced by new stellar arrangements formed by stars from our shifting solar neighborhood. Amid these changes, one celestial object will dominate the heavens, the Andromeda Galaxy, transformed into a breathtaking and ever-changing spectacle. Today, Andromeda occupies a modest portion of the sky, about the size of a fist held at arm's length. But as the millennia pass, Andromeda will loom ever larger, growing to fill the night sky. Its shape, once an elegant spiral, will become twisted and distorted under the influence of the immense gravitational forces binding it to the Milky Way. This cosmic entanglement will unfold over billions of years, culminating in a majestic and cataclysmic merger. The story of Andromeda's motion begins in the 1920s with Edwin Hubble's revelation that the Andromeda Nebula was not part of the Milky Way, but an entire galaxy unto itself, situated an astonishing 2.5 million light-years away. This discovery expanded humanity's view of the universe and established Andromeda as our closest galactic neighbor. Measuring its motion, however, proved to be a complex challenge. In 1957, Dutch astronomer Hendrik van de Hulst made a breakthrough using radio astronomy. By studying the faint 21 centimeters radiation emitted by neutral hydrogen in Andromeda, he mapped its movement. The results revealed a blue shift, a shortening of wavelengths, indicating Andromeda was moving toward us at an average speed of 296 kilometers per second. After accounting for the Sun's motion around the galactic center, the net motion of Andromeda toward the Milky Way was calculated at approximately 100 kilometers per second. This motion, however, is not unidirectional. In the context of the universe's expansion, both galaxies are moving toward a shared gravitational center, bound by their mutual attraction. It wasn't until 2012, when astronomers using the Hubble Space Telescope measured Andromeda's lateral motion, that we confirmed a direct collision course. The cosmic ballet between the Milky Way and Andromeda will begin in earnest about 2 billion years from now. As the galaxies draw closer, gravitational forces will stretch and distort them, creating phenomena that echo familiar tidal interactions on Earth. The parts of each galaxy nearest to the other will experience stronger gravitational pulls, while distant regions will feel weaker forces. These tidal interactions will elongate the galaxies, pulling entire spiral arms apart and forming immense tidal tails composed of stars and gas. This gravitational interplay will also spark intense bursts of star formation. Gas clouds compressed during the merger will collapse, igniting furious rounds of stellar birth at rates thousands of times higher than today. Bright, massive stars will dominate this new generation, their light and energy creating a dazzling display across the merged galaxies. Over time, bridges of stars and gas will form between the two galaxies, linking them as they spiral toward their eventual union. The collision of Andromeda and the Milky Way will not be a sudden, catastrophic event. Galaxies are composed mostly of empty space. Their stars are so far apart that direct collisions between them will be rare. Instead, the gravitational interactions will disrupt the orbits of stars, reshaping the flat disks of the galaxies into a chaotic, overlapping mass. Some stars will be ejected entirely, flung into intergalactic space by the immense forces at play. Others will settle into new orbits within the merged galaxy. The first pass of the galaxies will take over 100 million years, followed by a series of collisions and separations over the course of several hundred million years. Each encounter will compress gas clouds, triggering fresh waves of star formation. The final stages of the merger, occurring around 5 billion years from now, will see the Milky Way and Andromeda coalesce into a single, unified structure. Astronomers predict the resulting galaxy, often dubbed Milkomeda, will be a massive elliptical galaxy, marked by a dense central core and a smooth, featureless halo of stars. The brief era of intense star formation will eventually end as the galaxy's gas reserves are depleted. The young hot stars will burn out quickly, leaving behind long-lived dim red dwarf stars. Milkomeda will fade into a quiet red-hued existence, its days of stellar brilliance behind it. The merger will also leave an imprint on the surrounding environment. Streams of stars and gas, remnants of tidal interactions, will extend far beyond the boundaries of the new galaxy. These structures, known as stellar streams, will serve as evidence of the cosmic drama that unfolded billions of years earlier. Beyond the Great Attractor, a cosmic odyssey. Mathematics often serves as a crystal ball, offering insights into the distant realms of space and time. This narrative begins not in the laboratories of modern cosmology, but in an unexpected historical setting, revolutionary France. In 1792, Gaspard Monge, a French mathematician and minister of the Marine, sought solutions to logistical problems, aiming to optimize the transport of goods. Unbeknownst to him, his foundational work would ripple through centuries and disciplines, eventually contributing to our understanding of the universe's grand architecture. Decades later, André-Marie Ampère, celebrated for his work in electromagnetism, extended Monge's principles, crafting equations applicable to economic models, optimizing the allocation of resources between mines and factories. The practical utility of these equations found renewed purpose during World War II, when Soviet mathematician Leonid Kantorovich adapted and advanced Monge's and Ampère's methods to solve the Soviet Union's complex logistical challenges. However, it was in the 1970s that Canadian-American cosmologist Jim Peebles identified a far-reaching application of these mathematical tools, deciphering the mechanics of galaxy formation. Building on Peebles' insights, French astronomer Roya Mohaye and Russian astrophysicist Andrei Sobolevsky wielded the Monge-Ampère-Kantorovich equations as a cosmological crystal ball. They ingeniously reconstructed the past trajectories of galaxies by analyzing their current positions and velocities. Galaxies move under the influence of mutual gravitational attraction, and by leveraging our understanding of gravitational laws, the equations enabled a method to transport galaxies back in time. Although each step introduces increasing uncertainties, this technique offers a window into the cosmic past, mapping galaxies' journeys billions of years ago. Brent Tully and collaborators have since developed Cosmic Flows, a series of continuously updated catalogs charting tens of thousands of galaxies' motions. These maps not only illuminate the past, but also predict the future trajectories of galaxies, including the Milky Way. Through these efforts, scientists have unraveled the mysteries surrounding the Great Attractor, a gravitational anomaly influencing the motion of our galaxy and its neighbors. The universe's expansion provides a preferred frame of reference against which all motion can be measured. The cosmic microwave background, CMB radiation, a relic of the universe's infancy when it transitioned from a plasma state to a neutral gas, roughly 380,000 years after the Big Bang, serves as this benchmark. The CMB's near-perfect uniformity, with temperature deviations of only 1 part in a million, captures the universe's primordial homogeneity. Observing the CMB reveals a subtle dipole pattern, a slight blue shift in the direction of the constellation Leo, and a corresponding redshift toward Aquarius. This discrepancy stems from our motion relative to the CMB. The measured shift implies a velocity of approximately 600 kilometers per second. After accounting for the Sun's orbit around the Milky Way and the Milky Way's impending collision with the Andromeda Galaxy, a residual velocity of about 300 kilometers per second remains, pointing directly toward the Great Attractor. The universe assembles itself through hierarchical structure formation, beginning with galaxies. The Milky Way, born as a modest collection of stars, grew through successive mergers, a process mirrored across the cosmos. Groups of galaxies, such as the local group containing the Milky Way, Andromeda, Triangulum, and several dwarf galaxies, are gravitationally bound systems that continue to coalesce. Within 100 billion years, these groups will merge into a single mega-galaxy. Clusters of galaxies represent the next tier of this hierarchy. The Virgo cluster, the nearest major cluster, exerts a powerful gravitational pull on the local group. Over billions of years, this gentle tug has transformed into a formidable force, drawing galaxies inexorably inward. Yet, clusters are not the universe's largest structures. They themselves are components of superclusters, vast, loosely defined aggregations of clusters. In 2014, Brent Tully and collaborators redefined superclusters using the Monge-Ampere-Kantorovich framework. By mapping galaxies' motions, they revealed that the so-called Virgo supercluster is but a single branch of a far grander entity, Laniakea. Spanning over 500 million light-years and containing 100,000 galaxies, Laniakea's name, meaning immense heaven in Hawaiian, reflects its vastness and beauty. The local group belongs to the Virgo branch, which in turn is part of Laniakea. All are drawn toward a singular destination, the Great Attractor. The Great Attractor's influence emerges from billions of years of cosmic evolution. Situated at the heart of Laniakea, it represents the culmination of gravitational interactions across unimaginable scales. While its exact nature remains shrouded due to its location in the zone of avoidance, a region obscured by the Milky Way's dense disk, observations suggest it is part of a massive cluster or supercluster complex. The Great Attractor epitomizes the dynamic nature of the universe. Galaxies, clusters, and superclusters are not static structures, but living entities, shaped by ceaseless motion and interaction. This intricate dance, governed by gravity, began in the universe's earliest moments and will continue for billions of years to come. Our understanding of the Great Attractor remains veiled, obscured by the so-called zone of avoidance, a region of the sky rendered inaccessible to visible light telescopes by the dense dust of our own galaxy. Yet certain wavelengths, radio, infrared, and X-ray, possess the ability to pierce through this cosmic shroud. With these tools, astronomers have managed to glean glimpses of what lies beyond, revealing fragments of the vast structures within the Great Attractor's domain. At the heart of Laniakea, the immense supercluster housing the Milky Way and approximately 100,000 other galaxies, lies the Norma cluster. Named for the constellation through which it is observed, the Norma cluster sits roughly 220 million light-years away. This massive structure, several times larger than an average galaxy cluster, forms the focal point of our galactic migration. Despite traveling at speeds exceeding 100 kilometers per second, it would take the Milky Way more than 100 billion years to reach Norma's gravitational embrace. Like all galaxy clusters, Norma's formation is the product of countless mergers and the inexorable pull of gravity. Uniquely, it occupies the bottom of a colossal gravitational well, serving as the central attractor for this region of the universe. Over time, Norma will continue to grow, gathering material as its influence deepens. Yet, even as it looms large in our understanding, recent surveys employing advanced techniques, notably the Monge-Ampere-Kantorovich reconstruction, indicate that Norma's role is not the final chapter in this story. While the Norma cluster dominates locally, its gravitational pull falls short of accounting for the observed velocities of galaxies within Laniakea. This suggests the existence of an even larger structure, deeper in space, the Shapley supercluster. Discovered in the 1930s by Harlow Shapley, this massive entity lies over 650 million light-years away. As one of the universe's largest known superclusters, Shapley exerts its gravitational influence across hundreds of millions of light-years, dwarfing the scale of Laniakea. The Shapley supercluster's incredible mass hints at its significance as the next major destination in the cosmic flow. If the universe's vast movements continue unabated, Laniakea itself will ultimately collapse into a single massive structure, a supersized Norma cluster, which would, in turn, converge with Shapley's heart. The gravitational ballet between these immense entities underscores the layered complexity of cosmic evolution. The narrative of motion extends beyond these superclusters. In 2008, NASA astronomer Alexander Kashlinsky identified a peculiar phenomenon using data from the cosmic microwave background, CMB. Known as the kinematic Sunyaev-Zeldovich effect, this signal arises when CMB photons interact with the hot gas within galaxy clusters. Kashlinsky's analysis revealed a large-scale movement of clusters toward a point between the constellations Centaurus and Vela, a phenomenon he dubbed dark flow. This flow, with velocities ranging between 600 and 1,000 kilometers per second, encompasses vast portions of the observable universe. However, the mystery of dark flow deepens when considered against current cosmological models. The observed density variations in the universe appear insufficient to generate such coherent large-scale motion. While the ESA's Planck satellite later cast doubt on dark flow's existence, the debate persists, emblematic of the enduring enigmas that define the cosmos. The forces shaping the universe are not solely contemporary. Imprints from its earliest moments continue to resonate, influencing the large-scale structure we observe today. When the universe was in its infancy, a hot, dense plasma, sound waves known as baryonic acoustic oscillations propagated through the medium. As the universe expanded and cooled, these waves froze in place, leaving behind faint imprints in the distribution of matter. Recent surveys have uncovered these echoes, most notably a vast, shell-like structure named Ho'olelana. With a radius exceeding 400 million light-years, this formation encompasses features like the Sloan Great Wall and the Boats supercluster. Brent Tully and collaborators, who identified this structure in 2023, suggest it represents a single baryonic acoustic oscillation, a remnant of the primordial universe's chaotic symphony. The Hawaiian name Ho'olelana, meaning murmurs of awakening, poetically captures the essence of this ancient relic. Gravity's role in the universe is complemented by an opposing force, repulsion. Among the most intriguing manifestations of this phenomenon is the dipole repeller, a vast void located opposite the Shapley supercluster. Unlike dense regions, which pull matter inward, voids like the dipole repeller exert a pushing influence, propelling galaxies away from their periphery. This counterintuitive behavior is driven by the void's content, dark energy, which dominates its vast expanse. The dipole repeller's influence adds a new dimension to our understanding of cosmic motion. It suggests that the universe's structure is shaped not only by gravitational attraction, but also by the interplay of repulsive forces. Over time, these dynamics will unravel the cosmic web, preventing galaxies from converging at focal points like the Great Attractor. Instead, the universe will become increasingly diffuse, its grand structures dissolving under the inexorable influence of dark energy. The story of the Great Attractor and its neighboring structures is one of perpetual motion, a symphony conducted by the twin forces of gravity and dark energy. From the veiled depths of the zone of avoidance to the vast reaches of the Shapley supercluster, the cosmos reveals itself as a dynamic, interconnected tapestry. As we unravel these mysteries, we find ourselves not only mapping the universe, but also engaging with its profound narrative, one of creation, movement, and eventual dispersion. The unfolding cosmos, Einstein, dark energy, and the fate of the universe. In the annals of scientific history, there are few figures as towering as Albert Einstein. His intellect, often described as transcendent, propelled him to make groundbreaking discoveries that transformed our understanding of the physical universe. Yet, even a mind of his caliber was not immune to doubt and missteps. Among his many triumphs, there exists a curious detour, a mathematical addition born not from discovery, but from the weight of contemporary assumptions. This addition, famously called Einstein's greatest blunder, would later re-emerge as a pivotal element in our understanding of the universe's accelerating expansion. In 1915, Einstein unveiled his masterpiece, the general theory of relativity, a framework that redefined gravity not as a force, but as the curvature of space-time itself. With equations so elegant they seemed inevitable, Einstein provided a toolset capable of describing phenomena from the motion of planets to the bending of light by massive objects. Inspired by this success, he sought to apply his equations to the grandest scale imaginable, the entire universe. At the time, prevailing wisdom held that the cosmos was static and unchanging, a serene expanse where galaxies and stars might move locally but remained collectively at rest. When Einstein plugged the mathematics of general relativity into this cosmological picture, he encountered a perplexing result. The equations resisted stasis. They demanded dynamism. They suggested a universe that was either contracting under its own gravity or expanding outward in an unrelenting sprawl. For Einstein, this conclusion was unsettling. A dynamic universe clashed with the philosophical and scientific conventions of his era, and he hesitated to challenge such entrenched beliefs. In the 1920s, Edwin Hubble's observations of distant galaxies revealed that they were moving away from us. Moreover, the farther a galaxy was, the faster it receded, a relationship now encapsulated in Hubble's law. The universe was not static, it was expanding. The cosmological constant, introduced to maintain stasis, was rendered unnecessary. Einstein, recognizing his error, reportedly called Lal his greatest blunder. The term faded from prominence, relegated to a historical footnote. Yet the story of the cosmological constant was far from over. Decades later, theoretical physicists revisited Lal in light of advances in quantum mechanics. The vacuum of space, once thought of as empty, was revealed to be anything but. Quantum fluctuations filled the vacuum with a seething energy, a vacuum energy that imbued even the emptiest reaches of space with a subtle but pervasive influence. Remarkably, this vacuum energy was mathematically equivalent to Einstein's cosmological constant. Though discarded by Einstein himself, Lal had found new theoretical footing. The true vindication of the cosmological constant came in 1998, when two independent teams of astronomers announced a startling discovery. The expansion of the universe was not slowing down, as might be expected from gravitational attraction, but accelerating. This acceleration, observed through the dimming light of distant supernovae, pointed to the presence of a mysterious force, dubbed dark energy, that counteracted gravity on cosmic scales. The most plausible explanation for dark energy was the vacuum energy of spacetime, a concept eerily reminiscent of Einstein's long-abandoned Enlil. Today, dark energy accounts for roughly 70% of the universe's total energy content. It dominates the cosmos, shaping its destiny in profound and unsettling ways. To understand this influence, we must trace the cosmic timeline. For billions of years after the Big Bang, the universe was governed by matter and radiation. Gravity, stemming from the clumping of matter, acted as the principal architect of cosmic structures. Galaxies formed, clustered into groups, and coalesced into vast superclusters like Laniakea, our local region of the cosmic web. But as the universe expanded, its matter grew increasingly diluted. Around 5 billion years ago, the density of matter fell below that of dark energy. This moment marked a profound shift, the era of dark energy dominance. Dark energy, tied to the fabric of spacetime itself, behaves differently from matter. While matter disperses as the universe expands, dark energy appears to increase, filling the growing void with ever more intensity. This feedback loop drives the accelerated expansion, stretching the cosmos at an ever faster rate. As a result, regions of the universe are being torn apart. Galaxies that are not gravitationally bound to one another are receding faster than the speed of light, effectively disappearing from view. The cosmic web, once an interconnected tapestry of galaxies and filaments, is unraveling. The voids, vast, empty regions of space, are the front lines of this cosmic deconstruction. Filled with little more than dark energy, these regions expand at an accelerated pace, driving the galaxies at their boundaries farther apart. Over time, the voids will merge, leaving behind isolated islands of gravitationally bound structures. Our local group, containing the Milky Way, Andromeda, and a few dozen smaller galaxies, will endure. Over billions of years, these galaxies will merge into a single elliptical galaxy, a solitary beacon in an otherwise dark and empty universe. Clusters like Virgo, dense with thousands of galaxies, will also survive, but the larger superclusters, including Laniakea, are doomed. They lack the cohesion to resist the relentless pull of dark energy. The ultimate fate of the universe hinges on the nature of dark energy, a mystery we have yet to unravel. If dark energy remains constant, the cosmos will continue to expand forever, growing colder and darker as galaxies exhaust their fuel and stars wink out. This is the heat-death scenario, where entropy reaches its maximum and no useful energy remains. If, however, dark energy increases in strength, the universe faces an even more dramatic end, the Big Rip, in which the accelerated expansion tears apart galaxies, stars, planets, and even atoms. Whatever the outcome, dark energy ensures that the universe will not rest. It is the force driving the cosmos into an ever-expanding future, a relentless agent of change born from the vacuum itself. Einstein's cosmological constant, once a tool to preserve stasis, now serves as a reminder of the dynamic and ever-evolving nature of the universe. As we gaze into the depths of space, we are not merely witnessing distant galaxies, we are observing the forces that will shape the ultimate destiny of all that exists. The future trajectory of the Milky Way is intertwined with that of the local group, bound on a seemingly inevitable collision course with the Andromeda Galaxy. This cosmic dance, though dramatic, offers little solace against the inexorable pull of larger forces that shape the universe. Even as we chart this impending merger, the local group's fate appears to be one of isolation, unable to reach the gravitational sanctuary of the Virgo cluster or the enigmatic Great Attractor. Instead, the local group will succumb to the accelerated expansion of the universe, a consequence of dark energy's relentless influence. Distant galaxies and clusters will dim, their light fading as they cross the cosmological horizon, beyond which they are forever lost. Hundreds of billions of years from now, the local group will have coalesced into a singular mega-galaxy, adrift in an expanding void. Over the course of trillions of years, this solitary island of matter will fragment further. Gravitational interactions will eject stars, one by one, into the abyss. Once these stars escape the gravitational clutches of the megagalaxy, they too will succumb to the accelerated expansion, as if erased from existence. Gradually, the galaxy will dissipate, leaving behind an ever-dwindling remnant. This fate is not unique to galaxies, but applies universally. Over hundreds of trillions of years, every macroscopic object, from stellar remnants to planetary husks, will be cast adrift. The accelerated expansion of the universe ensures that these objects will become utterly isolated, separated by vast distances that grow faster than light itself can traverse. The faint glow of the cosmic microwave background will remain as a spectral echo of a universe once teeming with complexity. In this vast and empty expanse, the universe will approach a state of rest, its dynamics stilled by the unyielding hand of dark energy. On smaller scales, the interplay between quantum mechanics and information reveals another realm of inaccessible knowledge. Einstein, in his debates with Bohr, sought to challenge the fundamental indeterminacy of the quantum world, proposing thought experiments to argue that the uncertainty principle was an artifact of incomplete understanding. Yet, Bohr's meticulous rebuttals highlighted the inherent limitations of quantum mechanics and affirmed the principle's validity. Einstein reluctantly conceded the probabilistic nature of quantum phenomena, but maintained that quantum mechanics was an incomplete description of reality. At the heart of this indeterminacy lies the Schrödinger equation, which governs the evolution of quantum systems. Unlike classical physics, where the future behavior of a system can be determined precisely from its initial conditions, quantum mechanics offers only probabilities. Every particle is associated with a wave function, a mathematical description of its likelihood of being found in a particular state. The wave's peaks and troughs indicate regions of high and low probability, but they provide no definitive answers, only possibilities. Remarkably, quantum uncertainty extends beyond the subatomic realm. In 2019, researchers led by Jakob Fine at the University of Vienna demonstrated the wave-like nature of a molecule composed of 2,000 atoms. This groundbreaking experiment revealed that the quantum fuzziness, once thought confined to the microscopic domain, could manifest at surprisingly large scales, challenging our intuitions about the boundaries of quantum behavior. Beyond the reach of quantum experiments lies another inaccessible domain: black holes. These enigmatic objects, the densest repositories of information in the universe, are shrouded in mystery. A black hole's defining feature is its event horizon, an invisible boundary beyond which nothing, not even light, can escape. The contents of a black hole, the remnants of the stars it consumed, and any additional material it accumulated over time, are irretrievably hidden from the outside universe. While it is theoretically possible to access this information by crossing the event horizon, such an endeavor comes at a fatal cost. Within a finite amount of time, as measured by an observer's wristwatch, the traveler would reach the singularity, where the laws of physics break down, and any revelations gained would be lost forever. The information paradox posed by black holes underscores the limits of our knowledge. To an external observer, a black hole reveals only its mass, angular momentum, and charge. Everything else, the intricate details of its formation and history, is veiled in darkness. Similarly, the past itself represents an inaccessible repository of knowledge. While the present state of the universe reflects its history, the exact details of past events are irretrievable, accessible only through imperfect memories and surviving artifacts. As we confront these barriers to understanding, we are reminded of the finite bounds of accessible knowledge in the universe. The observable cosmos contains somewhere between 500 billion and 2 trillion galaxies, each hosting billions to trillions of stars. Even if we could instantaneously catalog every galaxy and star, this dataset would represent the entirety of information available to address questions about galactic and stellar evolution. Beyond these galaxies lies a vast ocean of particles and fields. The observable universe is estimated to contain 10 to the power of 80 protons, along with comparable numbers of electrons, neutrinos, and dark matter particles. Photons, primarily from the cosmic microwave background, number around 10 to the power of 90. Each of these particles carries information about the universe, but even their complete measurement would not exhaust the limits of accessible knowledge. To fully comprehend the universe, we must delve deeper, probing the quantum fields that underpin reality. These fields exist as vibrations in space-time and give rise to particles as localized excitations. At the smallest scales, these fields exhibit quantum fluctuations, a phenomenon known as quantum foam. The quantum foam represents the fundamental granularity of space-time, where energy briefly manifests as particle-antiparticle pairs before annihilating. This seething turbulence is most pronounced at the Planck length, approximately 1.61 times 10 to the power of -35 meters, where the smooth fabric of spacetime gives way to chaotic dynamics. The Planck length serves as the ultimate resolution limit to knowledge, a boundary beyond which our understanding falters. By dividing the observable universe into Planck scale units, we can estimate its total information content. Advanced theories, including those inspired by Claude Shannon's work on entropy and information, suggest that each Planck scale unit corresponds to a single bit of information. This approach yields a staggering estimate. The universe contains approximately 10 to the power of 120 bits of information. Despite this immense wealth of data, the universe imposes insurmountable limits on what can be known. Even if we were to achieve complete knowledge of the observable universe, questions would remain unanswered, constrained by the finite scope of accessible information. As we push the boundaries of exploration, from the vast expanses of cosmic structure to the intricate workings of quantum systems, we are confronted with the profound realization that the universe's mysteries are not infinite, but bounded. Yet, within these boundaries lies a universe of extraordinary depth and beauty, a testament to the power of human curiosity and imagination. In contemplating the ultimate limits of knowledge, we are drawn to wonder. Even if we could measure every particle, decode every quantum fluctuation, and chart the evolution of every galaxy, would we truly grasp the essence of the universe? Or would the act of understanding itself transform, revealing new perspectives and possibilities beyond the reach of our current imagination? The journey to answer these questions is as boundless as the universe itself, a testament to the enduring quest for knowledge that defines our place within the cosmos. The limits of infinity. When first introduced, the idea of true limits, of boundaries to infinity, was met with fear and resistance. For generations, it was dismissed, ridiculed, and even suppressed, viewed as heretical to the deeply ingrained convictions of a flourishing civilization. To entertain such an idea was to question the very foundation of their worldview, the boundless potential of exploration, knowledge, and mastery of the cosmos. Yet, as millennia passed, and no alternative path to ultimate understanding presented itself, the idea began to gnaw at the collective psyche of the civilization. What if their grasp on the universe was not incomplete because of insufficient effort or technology, but because the universe itself imposed insurmountable barriers to knowledge? By this time, the civilization was ancient, transcending the imagination of even their most optimistic ancestors. They had long abandoned the constraints of planetary existence, spreading their influence across the vast expanse of their home galaxy. Having encountered no other intelligent life, they reshaped their galaxy to their will, harnessing its energy, manipulating its matter, and achieving the once unimaginable status of a Kardashev Type 3 civilization, a society capable of wielding the energy of an entire galaxy. Yet even as they achieved unparalleled dominion, their progress began to falter. They found themselves constrained by limits they could not surmount. Their machines, built to think beyond human capacity, mirrored their creators too closely, and their insights were bound by the same frameworks and biases. Despite their technological triumphs, they remained tethered to their origins, their perspective shaped by the genetic and cultural heritage of their ancient past. Desperation gave rise to a radical plan to seed intelligence anew, untainted by their history, on a distant, unremarkable world. This world was chosen carefully. It orbited a stable star, was rich in the essential ingredients for life, and held the potential for biological complexity. The civilization intervened subtly, modifying the primordial conditions to encourage the emergence of life and, eventually, sapience. Encoded within the chemical precursors of life were deliberate tweaks, imperceptible but profound, to guide evolution toward consciousness. The architects of this project did not seek to control the outcome. They yearned for novelty. They slumbered through the eons, dreaming of the insights that might one day arise from this experiment, insights they hoped would break through their own limitations. The story of this civilization invites reflection on the boundaries of knowledge. Despite the monumental achievements of science, technology, and philosophy, there remain questions that defy comprehension. Even as humans, we grapple with profound mysteries: the nature of time, the origin of consciousness, the essence of existence itself. Science, for all its power and adaptability, may not be the ultimate tool for uncovering every truth. Indeed, before the scientific method emerged, knowledge was pursued through philosophy, mathematics, and introspection, approaches that continue to enrich our understanding of the universe. Consider mathematics, a domain where abstract truths are derived independently of the physical world. Mathematical axioms, once proven, remain true whether or not they have practical application. Similarly, philosophical traditions like skepticism probe the very foundations of knowledge, questioning whether we truly understand the universe or merely construct convenient illusions. Even within the physical sciences, there are limits to what we can know. Take the quantum realm, where uncertainty is a fundamental feature. The Heisenberg uncertainty principle dictates that we cannot simultaneously know both the position and momentum of a particle with infinite precision. This limitation is not a shortcoming of our tools or methods, but an intrinsic property of reality itself. On cosmic scales, the horizon of the observable universe imposes another barrier. Beyond this boundary, light has not had time to reach us, rendering vast regions of the cosmos forever inaccessible. And then there is the concept of infinity. It is both a tool and a torment for the human mind. Anaximander, one of the earliest philosophers to ponder infinity, posited that the universe was boundless. Later thinkers like Zeno of Elea grappled with its paradoxes, questioning whether motion itself was possible within an infinite framework. The advent of calculus by Newton and Leibniz provided a practical approach to handling infinitesimals, yet the philosophical conundrums of infinity persist. Mathematicians like Georg Cantor revealed that there are multiple infinities, an infinite hierarchy of sizes of infinity, but this mathematical elegance only deepens the mystery when applied to the physical universe. Modern cosmology introduces infinity in even more perplexing ways. The theory of inflation suggests that our universe is but one of countless others in a vast multiverse. Each universe within this multiverse may possess its own distinct laws of physics, particles, and forces. If the multiverse is infinite, as some theories suggest, then every possible configuration of matter and energy must exist somewhere within it. This includes an infinite number of worlds identical to our own, and an infinite number that differ in every conceivable way. Such a framework defies human comprehension and introduces the measure problem. In an infinite set, how can we assign meaningful probabilities or make generalizations about the nature of reality? Even if we were to transcend our current limitations, developing the ability to traverse the multiverse or access its hidden dimensions, we would face the ultimate challenge of infinity itself. The task of exploring an infinite multiverse would require infinite time and resources. No matter how far we journeyed, how much we discovered, or how sophisticated our tools became, the fraction of the multiverse we could explore would remain infinitesimally small. The pursuit of knowledge in such a context would become an eternal endeavor with no hope of completion. And yet, the limits of infinity are not confined to the vastness of the cosmos. They are woven into the very fabric of existence. At the smallest scales, the quantum foam, the seething, turbulent underlayer of spacetime, represents another frontier where knowledge reaches its limits. At the Planck scale, our understanding of physics breaks down, and spacetime itself becomes a roiling chaos. Beyond this scale lies a realm of speculation, where our theories may no longer hold sway. Thus, the ultimate limits to knowledge are both practical and philosophical. We are constrained by our biology, our tools, and the very structure of the universe. We can imagine overcoming some of these barriers through innovation and ingenuity, but others appear insurmountable. Even if we were to achieve perfect understanding within our observable universe, the infinite expanse of the multiverse would remain beyond our grasp. And so, we are left to ponder, is the pursuit of knowledge an endless journey, one that reveals ever more profound mysteries, even as it underscores our limitations?